for us about how expert software developers deal with errors. Can I have a big hand for Marian Petre?
Help?
What is it doing?
It's doing that. So, exit and do something, presumably? I did warn you. Hey, happiness. Goedemiddag. My thanks to Eric and the whole of the Joy of Coding team for inviting me here. Software rarely works as intended while it's being written. Things go wrong. Errors are inevitable. And a standard behavior in some software development is see the bug, swat the bug, and be done with it. In contrast, one of the things that I've observed over time is that for experts, error, or more generally, things that go amiss during software development, is opportunity. Opportunity to understand better, to question assumptions, to detect miscommunication or misconception, to stumble onto insight and innovation. Experts accept that errors happen. They're not fearful of error, but they are watchful. They often hold off swatting the bug, instead asking, that's odd, why is that? So indeed, error is seen as a useful input throughout the software development process, throughout the course of progressive development. So just to give you a glimpse of what's to come, I'll say a little bit about the research and evidence behind this talk. Everything I'm going to talk about is evidence-based. I'll provide a brief oversight of what we mean by active error, and then I'll spend most of the time talking through the kinds of perspectives and practices that I've observed in high-performing teams. So that you understand what I mean by high-performing teams, these are the guys who develop innovative systems that are delivered on time, on budget, no loud brown smells. The insights are interrelated, and you'll notice some repeated themes. Now, if you want to gamify this talk, I suggest you start keeping track of how many of the things that I'm going to talk about somebody else has mentioned already today, and see how many points you can get. So simply put, I pick the brains of software designers and developers, people like you. I've spent some 30 years studying experts and high-performing software development teams at work in industry across a range of domains in order to articulate their strategies, their reasoning, their practices. My purpose is to understand better the nature of software design and development expertise. So just to be clear, I'll be referring throughout the talk to teams and developers whom I've observed, but I'm hoping that you'll hear that as meaning people like you, who are fascinating to researchers like me. So in effect, I act as a kind of mirror or a lens, reflecting on what's there, focusing it. I'm interested in articulating what successful development teams do, not in dictating what they should do. And I should make it explicit here that I'm hoping, genuinely, that the talk will have some resonance with your experience, and indeed, if you have comments or examples, I would love to hear them. So research in software engineering predominantly considers error retrospectively, based on analysis of software in operation, usually on massive projects, usually in the context of a flaw left in the code that needs to be found and fixed, or of software system failures that arise from a collection of smaller flaws. You've all heard about the Swiss cheese model. We've been taking a more ecological view of error during software development, because one of the things that distinguishes high-performing teams is not that they make fewer errors, but they catch the errors during development before things go into, before things are released. In particular, we're paying attention to the smaller flaws, the things that go amiss, in order to understand the behaviors that allow developers to detect, identify, and recover from error. Now, the psychology literature offers the concept of active error, which is really what we're talking about. The human errors during a task, things that take the form of slips of action, things like typos, lapses of memory or attention, meaning that things get missed, mistakes made in forming intentions or in executing intentions during problem solving, so faulty decisions, inappropriate decisions. So for recovery, a developer must know that an error has occurred, must identify both what was done wrong and what should have been done, and then must understand how to undo the effects of the error and to implement what should have been done in the first place. So active errors might be caught in the act, but they may be detected a little bit later during standard checks and evaluation, by obstacles to progress, for environmental cues that supply feedback, or through unexpected outcomes. So in contrast to eliminating bugs as quickly as possible, experts reflect on the problem and on the solution model. So for example, from Tamara Lopez's work, a developer looked into what was initially seen as a straightforward bug. The fix was trivial, involving altering basic conditional behavior in a single function. Now, a root cause analysis might have interpreted this as a novice programming error, and it might have been, or more generously, as one of those things that just happens. However, the developer's experience suggested that the first explanation didn't make sense, and after deeper investigation, he found that this bug did not just happen, but instead may have had its origins several months earlier, shaped by decisions related to open source technology selection, the introduction of new communication channels, and design choices taken to meet demand-specific requirements. So the developer's greater awareness led from a simple bug to recognition of a deeper design flaw. So experts don't just fix the one bug. They recognize that a small bug may signal something more, rather than dismissing simple bugs as novice errors or as one of those things that just happen. And they stand back and they look for the other bugs that might hang out with it. And this is one of those things where if lots of little bugs are overlooked, little flaws, they can accumulate into something that can be catastrophic. So experts consider dependencies, they reflect on the code structure in order to understand whether the bug is part of a bigger problem. And thereby, they often detect other deeper issues, such as design flaws or miscommunications or misconceptions. Bottom line, as you know, software developers do not work in an ideal world. Rather, you're working in an environment dominated by conflicting demands and time pressures, conflicting priorities, and potentially conflicting stakeholders. So bugs are understood in the context of software use. Effective triage has to do with the cost-benefit assessment of the relative impact of the bug against the cost of fixing it. Bugs that aren't important are often tolerated or deferred. Software is kind of like laboratory apparatus. And in fact, in scientific software, they talk about their software as laboratory apparatus. It's tested for standard operating ranges. So for example, an oscilloscope is rated for the frequencies and voltages up to which it's calibrated, and for which its operation is reliable. Much software can similarly be understood to have standard operating ranges, and experts are attentive to the context in which it does. And they have an understanding of when it's okay to break the rules, and to tolerate bugs that are outside the usual range of the usual scope of operation. So for example, if you're considering something like a meteorological model, when assessing the stability of the model, it really doesn't matter if the temperature of Greenland is over 100 degrees centigrade. That's a different problem altogether. Brian Randall encompassed this in his concept of dependability because his definition leaves room for imperfection in the code if it doesn't impair the software's reliability. So tolerance is about managing the bug technically, in the sense of Randall's fault tolerance. But tolerance is also about managing the bug socially. leaving compilation warnings in the code as reminders, documenting the rationale. And in specific cases, such as safety-critical contexts, developers may wrap the code, preventing it from operating outside that reliable range. Related to tolerating is deferring, putting off addressing the error. Sometimes deferral is an outcome of triage. The error is not prioritized, but not forgotten. At other times, deferral is a design move. As one informant explained, and this is why I'm standing over here, because certain things are going to be direct quotations from informants. One way to solve a problem is just to ignore it for a while. Recently, I spent 2 18-hour days trying to solve this problem. At the end of the day, I took a long bike ride home, and halfway home, I had to stop. I realized the solution. The interesting step in the bike ride is that the developer left work. So thrashing is something that needs to be recognized. Thrashing is understood as poorly directed, ineffective problem solving. Both novices and experts thrash. Everybody thrashes at some point. The difference is that novices fail to realize they're doing it in good time and fail to break out of it. In contrast, experts recognize when they thrash. They break out of it by stopping the cycle, by example, for asking a colleague, by asking for help from colleagues. And there's evidence that with only a few days separation from the event, developers are able to articulate awareness of the positive and negative aspects of thrashing and to achieve some insight about the underlying problem. So stopping thrashing is one of the most effective ways of solving the problem that led to it in the first place. Similarly, developers have been shown to compromise at times in order to move work along. So their strategies may include deliberate suboptimal choices, calculated to serve immediate needs, enabling progressive improvement. In this case, an error may be connected to a working state, but leave the developer with a sense that, it's a compromise. You know, something's not right in the solution, or it's been achieved in a way that's ugly and unsatisfying. So one developer described compromising as a design strategy. In his words, we're developing an integration framework for composing AI and widgets for users, so the user can choose what kind of AI you want, what kind of widgets you want, update the dashboard live, and away you go. I know that in the long term, I need some sort of persistence mechanism. I could invest a lot in some huge complex database, or I could start out with a file, because that's not the problem I need to address yet. I need to address being able to say what sort of AI I want declaratively and be able to spin that up on a machine somewhere. I'm compromising by delaying that decision, by saying here's a little scaffolding, and I'll come back to that later. But it's enough to start addressing this larger problem that needs to be decided before I talk about persistence mechanisms. Some pieces need to be addressed first, but you need some scaffolding to even start. Once one piece solidifies, it informs the other pieces. So, my strategy for compromise is focus on the essence. Always shoot for the middle ground, building just enough so you can get going, and keeping it slightly general so that you can move forward. Compromising is a decision-making process for building. Then at the end, hopefully, you haven't compromised anything, and you've accomplished more than you might have hoped to. So I think this illustrates that developer strategies and responses to things that go amiss are fundamentally pragmatic. Software developers do not work in an ideal world, but rather in an environment dominated by conflicting demands and time pressures. Their strategies may include suboptimal choices, calculated to serve immediate needs and move things along, and behaviors that may appear naive or dysfunctional may not be. There are good reasons to try simple formulaic solutions before investing in systematic analysis. There are good reasons to buy time and potentially gather information and evidence by tolerating, deferring, or compromising. Crucially, you have to hear the crucially, high-performing teams keep track of those choices and revisit them. And they have safety nets. This one, experts mind the gaps. It sounds so simple. But rather than just looking for what they expect, they pay attention to the feedback and cues that might alert them to something amiss. They pay attention to the spaces between things, such as the interfaces, interactions between components, integration with other systems, domain concepts hidden behind standard data types. They pay attention to what isn't shown, what's missing, whether it's missing from the design or from the information or from the tool they're using. And this promotes detection of flaws, not just in the software itself, but throughout the development ecosystem. And that includes flaws in their understanding of the problem. For example, one team working on embedded automotive software was working on an engine control unit for a 1.4 megawatt engine. The team had done hardware-in-the-loop testing, and the actuator was simulated as part of that testing. When they put the real actuator in, it was nothing like the simulation, because unbeknownst to them, it was different from what was simulated. The internal control loop was faster than the specified control loop, and the developer reported, everything went bonkers! And so something was obviously wrong, and somebody hit emergency stop. As it turned out, the customer, who had specified the response times on the actuator, had been too aggressive, but the team had a control loop inside the controller, so the two control loops were fighting against each other, and the whole bench was literally rattling. As the developer said, this shows the value of hitting a problem with more than one hammer. Experts challenge assumptions, models, designs, through mechanisms such as the skeptic in the corner, pair debugging, code review discussions, and in doing so, they're mitigating against biases in human reasoning, particularly against confirmation bias. So for example, in both naturalistic and lab studies of test case selection by Teasley, Leventhal, and Rollman, testers were 4 times more likely to choose positive test cases than negative ones. That is, they were 4 times more likely to show that the program works than that it fails. So research evidence suggests that experts don't make fewer slips and minor errors than less expert developers. In fact, they make more. But they have better safety nets. So whereas many people look for evidence that things are working as expected, experts in high-performing teams are more available to contrary evidence. And indeed, their practices prime them to look for it. They seek evidence, they ask why, they engage users, they decorrelate, they elicit and contrast different perspectives. They seek falsification. They don't ask just how would I know if this is right, but how would I know if this were wrong? How would I know if an alternative were better? Importantly, they understand that the code is read by people, and they write comments about what is not in the code. So they write about their intentions and assumptions. They don't just write interpretations of code. Understanding something by breaking it is an analytic. Introducing flaws or errors deliberately can be a way of gaining insight into system operation. This is very familiar to testers. But experts who have experience of doing that intentionally to test their system also see unexpected breakage as a potential analytic and seize the opportunity to use it. For example, one developer was commissioned to do performance and scalability testing of a 20,000 node distributed client-server application. The chief architect was convinced that the system did work and that it would work at scale. There were 3 main environments: the developer test environment, pre-production, and production. Both the developer test and pre-production environments were supposed to be fit to use for performance testing. But in practice, there was no availability, there were no software tools to perform the performance testing, and so on. So the consultant developer was effectively blocked from doing what he was hired to do. And as it was a client-server system, entirely designed, written, and implemented by the team who worked for the service provider, someone would have to write or find a suitable tool to perform protocol-level performance testing. Now that led to an opportunity to learn about part of the system, the file transfer service. While trying to analyze the behavior of the file transfer service, the consultant developer entered commands manually via a software interface, and he inadvertently miskeyed the protocol messages. The kind of slip that happens. This led to unexpected behavior. The system exposed sensitive information, indicating that there might be major flaws in the implementation. The responses from the protocol, a server service, provided an opportunity to go and read the source code of the file server and to talk with the developers of that code. Special clearance was obtained to give the consultant access to the pre-production environment, and one of the Perl scripting gurus offered to code scripts to accelerate the testing manifold. This gave them an interactive mechanism to quickly probe the server. They could tweak and refine the script, they could run it, see what the results were, discuss the results with various people, and so on. Their scripts demonstrated that they could create and replace arbitrary files at the destination. The destination could be almost any or all of the nodes of the system. Some serious, significant issues with the software. A number of categories of test cases were designed and implemented. As you can see, they address familiar flaws, but flaws that had not been exposed by prior testing. When new flaws were discovered, suitable tests were created to ensure that the fixes could be tested effectively and efficiently. And similarly, their scripts were run in the production environment, showing that production was vulnerable and demonstrating that buffer overflow occurred. The script also created a marker file on the target computer. So the two of them worked as a pair. Pair debugging helped them work quickly and efficiently, despite all of the organizational boundaries that had held things up. So how can you verify that an analysis tool is doing what it's meant to? Experts reflect not just on their code, but on their tools as well. They play methods against each other to increase the likelihood of detection, so building errors into code to test the test harness. Experts address tool limitations by combining or swapping among tools. To quote one developer, often it's the mishmash of different ways of thinking that gets you the answer. So here's an example provided by an informant. I'll give you a moment to scan it. And to repeat a quotation from a previous story, this shows the value of hitting a problem with more than one hammer. Multiple techniques or tools may imply more ways to think. However, they also entail greater cognitive overheads. They require intelligent coordination. So the selection of tools is not arbitrary. Teams try tools, assess their merits, assemble toolkits that both fit their development culture and span different perspectives. One of the things that really distinguishes the high-performing teams is this business about continually reflecting on what they're doing throughout the development process. Experts reassess the landscape and deliberately expand the search space all the way through the process. Bill Curtis said, "Writing code isn't the problem. Understanding the problem is the problem." In a study by Curtis Krasner and ISCO, domain knowledge was identified as one of, if not the primary factor related to the success of a software system. So if your code isn't working, maybe you don't understand the problem. This business of standing back and reflecting on the landscape is crucial. We all know of examples where the software met its specification, but the specification was inadequate. Peter Ladkin commented on the 2015 Airbus A400M crash in Spain. That might have been the first aviation accident whose cause was directly attributable to a software error, because until then, all the software errors were actually requirements errors. That is, the software did what it was required to do, but what it was required to do was incorrect or incomplete. For example, not considering the effect of a second failure. In another example, Daryl Ince documented the failure of a record-keeping system that was rolled out across the UK to social workers. What was provided was a form-based system that required and constrained entries to a number of specified fields. Classic data entry, right? The result was that instead of spending 80% of their time with clients, the social workers spent the majority of their time wrestling with this unwieldy system. The software met its specifications, but it was not fit for purpose because it was specified by the wrong stakeholders. So reassessing the landscape is a way of examining barriers, understanding constraints, revealing assumptions, looking beyond the immediate issues, and reasoning about the essence of the problem and what might constitute a solution, and hence potentially admitting more potential solutions, potential innovation, broadening the definition of the problem in a way that provides insight and overcomes flaws. And experts do this periodically throughout the development process, not just at the beginning. And that's at odds with lots of software development methodologies which are trying to converge to a solution and keep people on a track. So sometimes these teams step away from methodology, actually pretty regularly. As part of assessing the landscape, experts keep an eye on their goals, and they distinguish between their goals and the tools they use to meet them. This is in contrast to what has been called metrics servitude or error by proxy, when, as Mike Hoy expressed it, people so easily fall into the trap of aiming for the metric instead of aiming for the result. Or as Richard Hamming expressed it, you get what you measure. I'm not the first one to quote that today. As Hamming said, accuracy of measurement tends to get confused with relevance of measurement, much more than most people believe. That a measurement is accurate, reproducible, and easy to make does not mean it should be done. Instead, a much poorer one, which more closely related to your goals, may be much more preferable. High-performing teams match their tools to their purpose and goals. They swap between tools or put them down as needed, and this includes tools such as methodology and notations. Mauricio Amiche gave an example regarding the use of code coverage tools in testing. His advice was, first write the tests based on the specification, then use a coverage tool to look for the gaps. So use code coverage to augment your test suite as a tool, not as a target. In the words of one developer, we use code coverage as a way of measuring what functions have not yet been tested. But it can't assess the quality of the test case itself. I can write a test case for a function and get code coverage, but the test case could be lousy and not test anything. We use code review, that is, dialogues about code, to assess the quality of the test case itself. Code review is about testing the intentions of the function. What should this thing be doing? So as mentioned in one of the previous stories, pair debugging is something that most of the high-performing teams do, and people don't talk about a lot. In the teams that I've studied, don't see that much pair programming, but I see pair debugging on a regular basis. They sit together and talk through code, often deliberately with people of notionally different levels of expertise or who know different parts of the code base. This brings a fresh perspective to the code, it spreads knowledge of the code among the team, and it has a tendency to expose assumptions, misconceptions, and miscommunications. One organization I observed understood these benefits and used pair debugging and collaborative code review as onboarding mechanisms. They assigned a variety of pull requests to the new recruit. The pull requests were selected to cover issues distributed across the code base. And in the course of addressing the requests, the recruit engaged in pair debugging with different members of the team, became familiar with both the structure of the code base and the expertise of the team, all in the course of doing real work. Experts don't expect to know everything. Indeed, most of them deny that they are experts because they are aware of the limitations of their knowledge. This is one of those tests, I'd go into a place and say, who's the expert? And I get pointed to, somebody, and then I'd walk over and I say, I understand you're the expert here, and they go, no. Pair debugging is one way that developers reach out, but more broadly, they're not afraid to ask questions, to ask people in their team, to ask people outside the team when they have a purpose to do so. They do it in different ways. One is just about having a conversation as a way of externalizing their thinking, and that's where things like rubber ducking come into play. Another is just understanding that they don't have to guess, they can ask. For example, one developer was working on the main control loop for a diesel engine controller. It was a standard proportional integral differential PID control structure, but with feed-forward adjustments, and in his words, the mathematics was correct, but proving it correct was way beyond me. So I found an expert in the engineering department of Cambridge University who was happy to work through the mathematics. Money well spent. Another developer said, the realization is you don't know everything, but there's probably somebody who might, and they don't wait to ask. So, we've covered a number of practices and perspectives that enable developers to embrace error, to realize it as opportunity, to understand, to question, to diagnose. There are repeated themes of attending to the big picture, not just to the bug, through reflection, minding the gaps, attending to contrary evidence, reassessing the search space. And within that, there are lots of different mechanisms to provide informative contrast and comparison. Again, repeated themes in expert behavior. So to sum up, experts use systematic, disciplined practices that are socially embedded and reinforced. Importantly, because there's a disciplined culture, they're able to rely on the team to catch slips. And that liberates individuals to experiment. So study of high-performing teams makes it clear that the interplay between designers plays a crucial part both in nurturing creativity and innovation on the one hand, and embedding systematic practice and rigor on the other hand, and hence handling error effectively. The team culture which leverages individual strengths and multiple perspectives provides the safety net. So there's a caveat to this, and it's an important one. The focus is on fixing the error rather than fixing the blame. And this, again, is a really strong cultural element. The team culture matters. It embodies the mindset that sees error as opportunity, that embraces multiple perspectives, that reinforces practices such as triage, playing methods against each other, pair debugging, whatever, that routinely challenge understanding and assumptions. This helps strengthen and develop the team as well as improving the software. Without that culture, teams can stagnate. Without that culture, groups of high-performing individuals may not cohere into a high-performing team. Put differently, software expertise doesn't happen by accident. There are practices that you can understand and invest in, and by making space in your organizational culture, and by investing time for this mindset, these sorts of practices, these dialogues, you're making space for expertise to work and grow, and for expert software development to become possible. Thank you for listening. I hope that this has given you a chance to reflect not just on your own practice, but on the talks that you've heard throughout the day. And again, if you have any comments or questions, or examples, or you want to be an informant for studies, I would love to hear from you.